Dear all, it is my great pleasure and honor to be with you in spectroscopy. And mashallah, Allah barik, based on the great success of the NMR, they asked me also to have a lecture about IR. We already discussed the NMR, one-dimensional and two-dimensional in Arabic and in English, as well as MS and LCMS, MS. So regarding IR, we'll take it in English and also in Arabic. So what about IR or infrared spectroscopy? This is a powerful technique which used in analytical chemistry, but especially to determine the functional group, المجموعة الوظيفية. So it is also can be used in polymer degradation and also with some other classes, but mainly the functional group. أساس المجموعة الوظيفية. And it can give really a vibrational spectroscopy. This is what we are going to determine regarding also the radiation and wavelengths. So it is between 4,600 centimeter minus 1. So this is a scale characterized for IR, very long range, of course. So let us go directly. If we take a spectrum like this IR, look to the range between 600 and 4,000. So this we call it IR spectrum. And we usually call it wavelengths or frequency. And the unit is centimeter minus 1. Here we can see this is peak, etc. What is the difference? Here we can say the intensity is a small, medium, and strong intensity. So this is regarding abundance. Therefore, if we take, let us go to some examples, then we explain the theory. But just to know about stretching and bending, there is two types. If we can say what means stretching and bending? Stretching is the vibrational occurring along the line of the bond that changes the bond length. And it doesn't occur along the line of the bond, but it changes the bond angle. It also, the diatomic molecule can undergo only stretching vibrational since it has no bond angles. What about bending? It is containing, if it containing 3 or more atoms are more complex. So such molecule can experience symmetric and asymmetric. So the molecule give symmetric peak and asymmetric. Also, it gave stretching peak and bending peak. We will take an example to explain more. So that's why the vibrational can be stretching and bending, two types of the same peak. Stretching and bending. Again, stretching is symmetrical and asymmetrical. So symmetrical like this way, asymmetrical like this way, and usually symmetrical is low IR frequency, while asymmetric is higher frequency. While in plane bending, out of plane bending. In plane bending, it is like this example. So you can see here the 2 atoms, while the carbon like that, it is active. And out of plane bending vibration, it is opposite way. So this is the difference between stretching and bending of the same molecule. It is bending is a lower value. Stretching is a higher value of the same group, while asymmetric is higher value than symmetrical. This is what you need to know in very simple way. So if we go to the range, I think it's important to know the range between 600 to 1400 is a sigma bond, single bond, CC, CO, CN, right? In the next range, between 1,600, 1,800, it is a double bond, whatever CC, CO, CN. What do you expect about triple bond? It will be higher. That's why it is between this value, 2,100 to 2,300 about. And this is very logic. So increasing the wave number in centimeter minus 1 means increasing between sigma bond, double bond, triple bond. What about the highest frequency, the highest wavelength is the functional group, which is NH, OH, and special one is CH, which is asymmetric and symmetric, as we can see. So it is preferable to know the range for covalent bond. It is all the range between 600, 4,000. This is a characteristic of IR. And then the sharp band, it is between 2,200 to 2,400 is C triple bond C, C triple bond N. It is very characteristic. Again, we can say it in different way for functional group. OH, 3,400. NH, about the same. While CH, 3,000. CN is C triple bond N, 2,200. Carbonyl group is 1,715. C double bond C, CO. Therefore, if we take it in very simple way, like a amide group, for example, it will give two peaks. One, of course, of the NH, only one peak here, 3,300. If it is NH2, it will be two peaks. And then the carbonyl group, which is 1,650, right? This table, you can see, it is about specific groups with exact frequency. So the type of the peak, which is stretching, for example, of CH, and the bending, so stretching higher in frequency than bending, as I told you, right? So you can see such examples also about the functional group like NH, etc. You can practice on such values, but don't memorize it. The scale which I showed you in simple way is the most important. Let us take some examples like alkanes. You expect to see CH in higher wavelengths plus CH2, CH3 in the lower one, which is in the range of 1,300 to 1,400. So this is what we will see. Stretching and bending. Stretching at higher delta, at higher frequency. Bending at lower frequency. Now you know it. So this is, for example, the CH of stretching and then CH2 bending, right? Very easy. That's very good, right? So now it is easy for you. If we take alkenes, what you expected to see? The CH, which is stretching, then the bending, which is lower value, and the double bond, which is in the middle value. So three types of peaks, stretching and bending, while C double bond C is in the double bond region. Let us take example like this peak. You will see it stretching here, CH2 at 1,400, C double bond C at 1,600, right? So now, and it is out of plane bending, again, you will see the four type of peak. I think is easy now, right? By the way, this is the old machine which you prepare the sample by putting it in potassium bromide plate. But the new machine, you don't need plate. You can put your sample directly. Then what do you expect about 3 triple bond C? This is characteristic peak at 2,150. And only one peak in this case. Like, for example, here, C triple bond C, you will see it is stretching here. But of course, you will see the bending as well of CH, not CC. CC, C triple bond C is only one peak. But if you have hydrogen attached, then you will see CH bending in this region. What about aromatic? Aromatic, again, you have CH stretching at higher value, C3000. You have the CH out of plane in bending in lower value. You have the out of plane. You have the double bond as well. 4 types of peaks as usual, which is in higher value, in the middle, and in the lower, which is out of plane bending, right? So if you take about this aromatic, you will see stretching here, right? Then C triple bond C at 2 peaks at 1,450 and 1,600. Then out of plane bending at lower IR value. يعني هنا بيبقى ليك 4 أنواع من البيك. عند stretching العالي اللي هو 3000، وبعدين الدبل بوند لها 2 بيك، وبعدين اوت اوف بلين بيندنج لها بيك. يعني واحده في المنطقه العاليه قوي، وبعدين المنطقه المتوسطه، وبعدين المنطقه القليله. طيب if you take another example, you will see practice the same way. Higher delta value, then C double bond C and out of plane bending at the lower one. So you can practice also about meta substitution. It has 3 different peaks. Of course, here is the ortho substitution is only 1 peak in out of plane bending. But if it is meta substitution, it is 3 peaks of out of plane bending, which is meta substitution. الاثنين في فرق بينهم كربونة. This is meta substitution. While ortho substitution means 2 peaks, 2 groups beside each other. It has 1 peak here. Then, if you have para substitution, you will have again the same peaks, right? Only 1 peak here, but the difference, you will see it here in this region, which is characteristic. So you can even use IR for differentiation between ortho, meta, and para. What about OH group, like alcohols, phenols, etc.? You will see it as a sharp peak in this region, right? This is very characteristic, right? If it is 3OH. However, if this make hydrogen bonded, like in alcohol dissolved in a solvent, then you will see it a broad peak between 3,300 to 3,400. If you see the alcohol is dissolved in a solvent, you will see 3OH. And then you will see COH in this case, which is bending at this value, while stretching at this value, right? So now you can see here. So this is OH stretching. It is broad, right? When it is broad, it means it makes a hydrogen bonding. Then the other peaks you have been already practiced about it, CH stretching, and here carbonyl group, COH group, you will see it here in the lower delta value. Then CH3 at 1,300 something, and CH2 at 1,450. Again here, now I can hear you. Is it broad or sharp? Yes, it is broad. It means it is hydrogen bonded. And you can see here para substitution. This is a characteristic of para substitution, right? Then you see the CH3 at this value. So I think with practicing the spectra, you get to know a lot. What about OH stretching? So this you can see here, the hydrogen bonded. Here is the free OH. So the difference between hydrogen bonded is broad. Free OH is sharp. This is free OH again. Now it is clear for you, I hope. What about amines? When it is primary amine, like NH2, it gives 2 peaks in this region. If it is secondary amine, it will give a single sharp peak. If it is tertiary amine, it means no NH. It means no peaks. It means for amines, it is characteristic at this high value for only NH2 and NH. When it is N only, no peak you will see. So if we take primary amines, for example, now you can see 2 peaks here at higher delta value, which means it is primary amine. And of course, you will see CH2 and NH as well. Now you can examine yourself, right? This is sharp peak in this area. It is NH with blue, right? And here in this area, around 3000 is CH stretching. Oh, what about this peak? Huh. Now you know, C double bond C, etc. So with such example, you can practice. So as I usually say to my student, spectroscopy is practicing with first examples, then problems. Look here, it is only one single peak, which is NH, right? NH, no 2 peaks, it means it's only NH. What about this peak around 3000? Is the CH. Then the C double bond C has 2 peaks, 1470 and 1600. And then you see monosubstitution here as well in the bending area. Then what about tertiary amine? No NH. It means you don't see any peak here in the NH region. What about if you compare between OH and NH? This is OH, hydrogen bonding. NH2 is 2 peaks, no hydrogen bonding here. What about ethers? This, it comes in the, usually in the fingerprint region, which is CO and CH and CN. So it is usually give the peaks in the lower delta value because it is sigma bond, as I have explained before. دي الرابطة الأحادية اللي هي الرابطة الفردية، فبتدي في أول البيك. المنطقة دي بنسميها fingerprint region. So you can practice on here that the oxygen is in ether form. Why? Because you don't see OH here. It means it is in ether form and it is monosubstituted. CH, then what about aromatic? 2 peaks in this region. Yes, now it comes to carbonyl group. It is characteristic because it gives sharp peak between 1690 to 1810. دي منطقة مميزة قوي للكربونايل لأن دي بتدي بيك شارب في المنطقة بس دي اللي هي موضحة قدامكم. طب لو كانت بالأول started with amide, carboxylic, ketone, aldehyde, ester, anhydride, acid chloride, anhydride. So for anhydride, it is 2 peaks for carbonyl. Why? Because this has 2 carbonyl group, so it gives 2 peaks. الانهيدرايد لها 2 كربونايل وبالتالي تدي 2 بيك زي ما حضراتكم هتشوفوا دلوقتي بعض الامثله. So now we can practice is if it is this compound, it is sharp peak here, so it is carbonyl group and it is in the form of aldehyde. And this is the CH stretching. Here is the ketonic group at 1700 about. So very characteristic and sharp. As we said, the IR mainly for functional group like carbonyl, OH, NH, NH2, NH, carboxylic group. Here is carbonyl group as a ketonic, then you will find it here. Now it is ester group, then it is more than carbonyl group at 1735. So this is a carbonyl group of the ester, for example, and the aromatic. Now you practice a lot with it. Here is the ester group again. So you see very sharp peak. This is what I would like to illustrate. Acid anhydride is very characteristic because it has 2 carbonyl group. So when it has two carbonyl group, it gives two peaks. This is very characteristic for anhydride. Of course, again, it gives peak here, which is in fingerprint region. We call this area fingerprint region because it has CO, CC, CN. Another two groups in the carbonyl group, immediately we'll say it is anhydride. What about لو الأسيتايل chloride? It will have this peak acid carbonyl group. It will be in the higher range for conjugated chlorides, right? In addition to the bending in fingerprint region. So this is the carbonyl group, which is at high delta value because neighbored by chloride. هنا الأسيتايل كلورايد بيدي بيك عند عالي عند 1800. This is high 1800. Again 1800 for the carbonyl group. What about very characteristic, which is carboxylic acid? If it is carboxylic acid, then it take very broad peak. It started from about 2000 to about 2300 to about 3300. Very broad. Immediately we say you have carboxylic group because it is OH of carboxylic. So it must be carboxylic group. OH, which is this peak, the broad one is the OH, while of course the red one, carbonyl group. Because carboxylic group has two functional group. OH, which is this broad one. Carbonyl group, it is this sharp one. That's why it's the most characteristic peak in IR. If you see broad peak, immediately we say you have carboxylic group. Imides, it has the lowest one, the carbonyl group at 1630. That's why you have it here, CONH. It is the lowest. Another example, a carbonyl and NH2. Now you know it is two peaks for NH2. So if you say this example, two peaks for amide group, and here is the carbonyl at lower delta value, 1600. Here is the amide group at lower delta value again, and here is the NH. Aliphatic nitro compound. So cyanide group, this is very important. The cyanide group, it gives a peak at 2000, cyanide group at 2250. Very characteristic here. So for cyanide group, it is, you can identify immediately of such peak here at 2250. If you take this example here, 2250, you will see the cyanide group, very characteristic. So now it's clear for NMR, and you can solve this question. What is the effect? Conjugation affected by resonance. So for example, conjugation lowers the energy of a double bond, so the effect is observed in IR. Look for this carbonyl, double, sigma, double, conjugation. Here, double, sigma, sigma, no conjugation. So what do you expect? In case of conjugation, it is lower frequency. So it is low value, right? Low value. While here, it is higher value. Why? Because now it is isolated carbonyl group. Conjugation will lower the observed IR bond for carbonyl group of 20 to 40, right? So, for example, here NH2 at 1677, right? Here CH3, then what do you expect? And chlorine and nitro. Also, inductive effect are usually small unless coupled with resonance. So the inductive effect is lower unless it's coupled with resonance, like in this case, for example, a strong resonance contributor, then poor resonance contributor. So this effect as well. effect on IR, steric effect, usually not important in IR. The steric effect is not important in IR unless they reduce the strength of bond. So for example, here, for regroup, and here steric effect. So very small effect. So it is not like the NMR, the steric hindrance effect. يعني الستريك افكت ما بيأثرش قوي على الاي ار زي الريزونانس. What about strain effect like this? This is a strain effect. So changes in bond angle forced by constraints of ring will cause a single change in hybridization. So this is a carbonyl group at 1815. What about if it is 4-membered ring? It is lower. 5-membered ring, lower. 6-membered ring, lower. 7-membered ring, lower. So this is really a strong effect. So as bond angle decreases, carbon becomes more electronegative as well as less sp2. So it increases the frequency or wavelength. We study also the hydrogen bonding. It affects a lot because it makes broad, as we have seen. بتخليها شكلها عامل زي الحلة، يعني برود لو في عندي هيدروجين بوند. In solution phase, these effects are readily apparent. In gas phase, where these effects disappear, for example, this is the gas phase of 1-butanol. You see? This is a gas phase. You cannot, it's very difficult to see the OH. But here, steric hindrance of hydrogen bonding, as we talked before, but you can see here. So the difference in gas phase and not gas is very visible. Hydrogen bonding also can interact with other functional group at lower frequency, like in this case, the carbonyl group here, and the OH, it make hydrogen bonding, and then and this is the references you can see. And in Arabic, if we take it in Arabic, الأشعة الحمراء دي واحدة من أهم التقنيات بس للمجموعات الوظيفية في المركب العضوي. برضه بتستخدم في الطب الشرعي لتحديد تحليل البوليمر. بس ما أقدرش أجيب صيغة مفصلة عن الصيغة البنائية أو الجزيئية أو كل أجزاء المركب. لا، يلزمني NMR وماس. يبقى الاي ار بتديني فقط المجموعه الوظيفيه، لكن ما تقدرش تديني الاستراكشر كله، الصيغه البنائيه كلها او الصيغه الجزيئيه كلها. لا، محتاج NMR وLCMS. ولذلك دي محدوده للغايه. يبقى بستخدمها مع تقنيات اخرى. ليه؟ عشان اقدر احط الاستراكشر كله. ولهذا السبب تلاقي جهاز الاي ار مثلا يعني ب $4000، بينما جهاز الماس يبدأ من $200,000. جهاز الاي ار الان ام ار من 500,000 أو $400,000 الجهاز الكويس. يبقى هنا السعر مرتبط بالمعلومات اللي اخدها. ده سعره قليل ليه؟ لانه محدود للغايه، بس بيديني المجموعات الوظيفيه، وكمان ما بيلزملوش لا سولفنت ولا اي شيء، والمينتنانس بتاعه قليل. يبقى هنا الناس اللي بتدرس علم الاجهزه الانسترومنتيشن يبقى عارفين ان السعر بتاع اي جهاز مرتبط بالمعلومات اللي يديها لي. ففي حاله الاي ار فيل ليميتد عشان محدود للغايه عشان المجموعات الوظيفيه. كمان مش بيحتاج مذيبات غاليه، كمان مش بيحتاج مينتنانس عالي. يبقى ده بيخليه ايه؟ سعره رخيص. بس لازم استخدمه بحرص طبعا عشان اللمبه بتاعته. يبقى كل الاحتياط اللي اخده في الانسترومنتيشن ان انا احافظ على اللمبه بتاعته. هي دي اللي مهمه عندي. يبقى ده نطاقه محدود ويجب استخدامه مع تقنيات اخرى زي الحاجات اللي قلت عليها. تمام. ده بيعمل بشوف منه المكان اللي فيه البصمة الجزيئية عند مقارنة العينات. يعني أقدر أقارن عينتين ببعض نقيتين، أشوف العينة دي نقية يبقى أقول عينة تانية لو ادت نفس السبيكترا بالذات في المنطقة الفينجر برينت أقول إنهم نفس المركب. يبقى هنا ده استخدام تاني ليه، إن أنا أقارن عينة بعينة. عينة طالعة عندي نقية وعايز أقارن بينها عينة تانية، أقوم أحطهم فوق بعض وأشوف إن هم متشابهين تماما. طيب الحاجة التانية، طاقة الجزيئات بتساوي الطاقة الإلكترونية زائد الطاقة الاهتزازية زائد الطاقة الدورانية. طب الأشعة تحت الحمراء بتهتم بدراسة إيه؟ امتصاص الأشعة تحت الحمراء، لأنها بتسبب انتقال للذبذبات في الجزيئات. عشان كده بعرفه إنه إيه؟ التحليل الطيفي الاهتزازي. صح كده؟ It makes sense. طب ايه السكيل بتاعه، التدريج بتاعه من 600 الى 4000، رينج كبير جدا. عشان كده ده بيتوافق مع اهتزازات التمدد والانحناء للجزيئات العضوية. الاهتزاز في الجزيئات زي الروابط التساهمية في الجزيئات، بتهتز باستمرار. عشان كده بنقول إن الرابطة بين ذرتين لها طول معين، وبالتالي بنحدد متوسط، لأن الرابطة بتتصرف لو كانت مهتزة، حاجة مهتزة بين ذرتين، يهتز الرابط بحركات التمدد والانحناء. عشان كده بنقسم الجزيئات للاهتزاز بتاعها ده لقسمين: التمدد والانحناء، اللي هو الاستريتشنج والبندنج. وعشان اسهلها عليكم، ده الاستريتشنج ده اهتزاز بيحدث على طول خط الرابطة، عشان بيؤدي لتغيير طول الرابطة، وبالتالي ما بيحدثش على خط رابطة، لكن بتغير زاوية الرابطة. وده بيحدث للجزيء ثنائي الذرة أن يخضع فقط لاهتزاز ممدد. والاستريتشنج ده اللي بيبقى عنده طول موجي عالي. يعني مثلا السي اتش نقول لها ستريتشنج عند ال 3000. طب لها بيندنج فين؟ عند ال 600 لل 1300. يبقى ده البندنج بتاعها. ليه؟ لأن البندنج بيحتوي على اهتزاز الجزيء اللي بيحتوي على 3 ذرات أو أكثر تعقيدا. ده الفرق بينهم. وبالتالي الجزيئات دي بتواجه التمددات والانحناءات متماثلة وغير متماثلة. وغالبا يشار لاهتزازات بالمصطلحات الوصفية: صخرة ومقص واهتزاز وتطور. طب الأشعة دي بقدر استخدمها كمان في الحاجات الإيه؟ البروتين والبيبتيدات، زي الإيمايد مثلا عند 3300. طيب وده الاستريتشنج. والبندنج عند 1650. طب اهتزاز التمدد للكربونايل عند 1550. طب كمان ال NH تبان عند الأقل. وبالمناسبة ال NH2 لها 2 بيك، ال NH لها 1 بيك عند 3300. طب ال N بس ملهاش ولا بيك. يبقى بقدر أفرق بين الامين الاحاديه 2 بيك، عشان ان اتش 2 لها 2 بيك منطقيا. طب بقت ثنائيه، يبقى اذا ان اتش يبقى لها 1 بيك. طب ثلاثيه يبقى ان بس ملهاش ولا بيك في المنطقه العاليه اللي هي 3300. تمام. اتمنى ان انتم تكونوا استفدتوا من المحاضره ديت. آه، اتمنى ان انتم تكونوا استفدتوا من المحاضره دي. يا رب يوفقكم، وبنتظر تعليقاتكم. ويا رب يجعله علم ينتفع به. Please spread the lecture to the other students, and I'm looking forward for your constructive criticism. السلام عليكم. Thank you very much.